Oops. What did I do? Alright, cool. Yeah, so you have three parts of our system, right? You have the source side, which is this. Basically, you have some transmission lines or some lines that connect to the other system. So yeah, there's your source, there's your lines, and this side you have your load. Your source and your load could be connected in two possible configurations based on your exam. We could bring either one, right? The source could be either a star or a delta. Same too with the load, star or a delta. That's how they make sure and read the question properly and make sure you know which one they gave you. Right? The most popular one is when you have the source as a star and the load as a delta. The load as a delta. Normally we'll kind of load on a delta or a star. But the source most of the time will be a star configuration. Right, cool. Yeah, so what this also is saying, you have the certain angles. So we know the phase is 120 degrees apart from each other spatially. But with the phasors, this is normally 0. When you go in this direction, which is the anti-clockwise direction, that is the positive direction. And when you go in this direction, there's the negative direction. So yeah, that's how to keep that in mind. So if there's the reference at 0, if you go this way, 120, it will be minus 120. And if you go this way, from 0, it will be 120. If you keep going in this direction, this will be minus 120. And then this will be minus 240. But just know, from the reference, 120 to the left is positive 120, which is your C phase. And then 120 to the right will be minus 120, which is your B phase. Yeah, cool. Well, now we know this from before. So VAB, which is your line voltage, is VN minus VBN. Reason I put this here, just a pattern. So VX, Y will be just be V, XN minus VY. That is the pattern of way to see. And one thing to keep in mind, anytime you have a balanced system, the sum of the voltages and the currents will be 0. So if a question asks to show that the system is a balanced system, you just get the three phases, the voltages and currents, you just add them up in vector and phasor form and show them that you're getting 0 as the answer. If you're not getting 0, that means the system unbalanced. Yeah, cool. Right, so the first type of configuration we have is the Y configuration. So in the Y configuration, we have three phases. You have a reference, which is basically just ground. So first thing we'll start with is VA, which is the A phase, is normally taken as the reference, right? So one thing you have to get, which is this part here, which is circling, is the naming convention. So normally the arrows point out, which is like this, right? If the arrows point out, it pointing from N to A, or N to the phase, the voltage will be AN. So VAN, just like we did before with the VXY, it will be VA minus VN. So let's keep that in mind. The arrows pointing out will be, so if we go in N to A, is VAN. Just keep that in mind. That's very important. And then going across into, well, down here basically same thing. So it means X with respect to Y, as literally what it means, right? But let's know if it going out, for the phases, you always use VAN, and VAN will basically mean when the arrow going out. Yeah, cool. So now we have these things here, which is basically we went through just some. So VA, VB, and VC. these are your phase voltages. So you notice the angles 0, minus 120, and 120. Sorry, these are your lines. Right? These, no, that's correct. Yeah, these are your phases. That's correct. So the three phases are 120 degrees apart spatially. So the VM and all the VMs here just basically just telling you the value for it. Whether it's like 120 volts, 240 volts, whatever it is, just the value. Right? And just remember, if you have the magnitude of the phase voltages for a balanced system with a balanced source, they will be 120 degrees apart spatially. So 0, minus 120, and 120. So VC is 120, VB minus 120, and VA, which is the reference, will be at 0. So these are your phases. Cool. So then now to get your line, so you have three lines for the Y. So you have VAB, you have VBC, and you have VC. Okay, I'm right this up here. VC. So there are three line voltages. And to get them is the same thing as here. So if I want VAB, it'll be VA minus VB. If I want VCA, it'll be VC minus VA. And if I want VBC, it will be VB minus VC. So same calculation, right? That is in terms of the magnitude itself getting it from the phasor domain. So with this example here, this example. So you could repeat it for VBC and VCA. So VAB is VA minus VB, and well, they basically end up with this. Alright? And then you have this here. Well, we'll get to the adjustment. So what it's trying to say is that your line voltage is 30 degrees apart from your phase. Because this basically that V line is root 3 V phase. But this is in terms of the magnitude, right? The angle itself now will be 30 degrees off of your phase. So it's shifted, so which is what this is here. The line voltage leads the phase voltage by 30 degrees. So V line will be root 3 V phase plus 30. So you have three different angles. So you have 0 for VA, VB is minus 120, and VC is 120. So if these three phases, the line voltages for each of them would basically, you have to add 30 degrees to each of them to get that value. Right? So you have VA, VB, VC, 0, minus 120, 120. If you want to get the magnitude of the line voltage, you multiply the phase voltage by root 3 in the magnitude. And then the angle now, we basically just adding 30 degrees to each of them. So this first one here, if you had to get VAB, the angle will be 30 for your VBC, minus 120 plus 30, you get minus 90. And then this here, 120 plus 30, you get 150. So that will be the angle for your line voltage. For the three line voltages, that is. Right? Any questions here? So you should, well, we know the I line and I phase is the same value. Yeah. So any questions here? So you have your phase
No.
voltage. Phase voltage is 0, minus 120, 120. To get the line, you multiply the magnitude by root 3 and you add 30 degrees to each of the phases. That is based, and I line is equal to I phase. So it's the same value. But we get to this in a bit. Cool. Onwards we go. Alright, so this is summarizing what we did before. I had a lot on the slide, so we know this. So the line voltage leads by 30 degrees, and vice versa, the phase voltage will lag by 30 degrees, right? So we know this already. So let's break it up. So the V line will be root 3 V phase, which is your magnitude. And then the angle will be the angle for the phase plus 30 degrees. Okay? So you have your phase voltages, which VA and VB and VCN. So 0, minus 120, 150. So there's your phase. And the lines VAB, VBC, and VCA plus 30 degrees. So all these here, you'll get these here, and the magnitudes will change. Right? And the phasor form is basically the same thing. This is your reference. And your line voltage leads. So if this is VA here, or VN in this case, This will be VAB. So 30 degrees plus 30 degrees off. Next one, you go down here to minus. So it'll be 120 minus 120. And then basically you add, you get your phase. And same thing for this side here, which from here now, it will be minus. So it'll be plus 120 and then plus 120. And then you add 30 degrees, you end up with CA. Just remember this direction here is negative and this one here is positive. You gotta remember that, right? It's kind of like counterintuitive to what we're accustomed to. So just keep that in mind. If you get confused a bit, just know this way is negative, this way is positive. Yeah. From the reference as. Cool, and we continue. Alright, the phase currents now. So we know we have three phase currents, IAN, IBN, and ICN, and we have three line currents, IA, IB, and IC. Yeah. The phase currents, to get the phase currents, the magnitude of it is okay. We could get that. But the angle for it depends on the load. Because the source supply and current based on what the load needs. Yeah. The current is more of a responding variable, right? So the phase current depends on the load, power factor, or the impedance angle, all the same thing. The impedance angle is basically the same thing as your power factor angle, right? So if you take phase A as the reference, remember I and IN, same value, right? Your line and the phase voltages for the Y configuration is the same thing. So if you pick I as reference for some impedance angle theta, cos inverse power factor, or your impedance angle will basically be, remember Z is R plus JX. So if you have the tan inverse, that will basically be a impedance angle. All the same thing, both is the same value. Cool, so you basically have I phase angle minus your power factor, which makes sense because the current doesn't normally have your power factor in it. And then the other three, same concept, minus 120, 120. But now we're just shifted by the angle. Yeah. So if theta is more than 0, we know it's an inductive load. And then if theta is less than 0, it's a capacitive load. So the signs itself will change depending on the type of load you have. Alright? So that's how you will get the three currents. This theta is your impedance angle. Just remember that. Majority of the time, your values itself for the angles, for the current, will be negative. Cool? And that's the current part. So to get the currents, you have to know what the load is on the device. Yeah? If I give you a source alone, the most I might ask you is to plot the phasor for the voltage. I can't ask you to plot the phasor for the currents, because I have to get a load to know how much currents it pulling. Yeah, because a source need a load, right? If you have a battery by itself, you're not gonna know what the current is, because it's just a battery. So you have to connect it to a circuit. Right, delta configuration. So the delta is basically kind of like the opposite of a star, but everything it did for the voltage part, you basically just gonna do it for the current part. And the voltage part will be the same thing as the current part for the star. You basically just swap it. So just like before, you have your three voltages. You have VAB, VBC, and VCA, just like before. And they shifted 120 degrees apart. Yeah. In this case, in a delta, your line voltage and your phase voltage is the same value. Yeah, it's basically the same value because your line and phase for delta is the same, which is why this VAB is equal to VP. So the voltages are shifted 0, minus 120, and plus 120 degrees. This will be the same. So if you're plotting a phasor for the voltages in a delta, remember there's our source, right? Because the current's leaving. It'll basically be the same thing. You won't have any shifts or anything, right? So that's basically what this thing here. So we have VA, VB, and VC, which is the same thing on top here, right? Your three lines. Your currents now is where the founders happen, just like with the voltages for the star. So IAB, which is basically will be equal to IA minus IB. So same concept as the voltage. So if you use IA as the reference, IAB will basically be at 30 degrees. It's the same concept, same thing. You just instead of using V, you're using I. Same equations. It's literally same equations, right? So instead of the voltages being shifted by 30 degrees between the phase and the line, for the delta, the current's gonna be shifted by the 30 degrees for the phase and the line. Yeah, because in a delta, the line current and the phase current not the same value. If it's not the same value, it will have the 30 degrees. If it's the same value, it will not have the 30 degrees. That's literally how you could remember it. Different, you'll have a 30-degree shift. Same, no 30-degree shift. It's cool. Let's go and continue. Slides. Cool. So for the delta, the first thing, use an impedance. So the phase currents, remember your currents, you need to know what the load is. Remember there's a delta source, currents leaving. Just keep that in mind. You need to know whether it's a source or a load. A load does consume current and a source does produce current. So yeah, I don't know which one it is. Yeah, so the phase currents, you need to know what the load is to know what current it's pulling. So you have three of them. So you have IAB, IBC, and IC to A, which is equal to I phase, and you have these three. So now you need to know what these are. Anytime you see theta, you're basically talking about your load angle. That will never change, right? So your three phase currents, which is the currents in the phase of the delta, basically be shifted 120 degrees, and it's shifted by the load angle. That will never change. But now, since we're doing the delta and the delta currents are not the same, that one will have the 30-degree shift in it, which will be different from the star. And now it's just the opposite to the line currents now. Instead of you adding 30 degrees like with the Y, you will just be subtracting 30 degrees to get your line currents. But notice it have the theta in it. Okay, can't change that. This here will basically be equivalent to the angle for the phase. So you can't change that. Right? Initially you'll have all these three as just fixed values. Meaning you will know what minus 120 minus theta is. So you're using those angles and then minus in 30 degrees from that angle. Yeah, you don't have to calculate this over again. Yeah. Reason being because your lines have your load angle part of it, and also it will have the shift. Yeah, you just have to know which one the 30 degrees in. For the Y, the 30 degrees is the voltage. The voltage do not have the load angle in it. For the delta, the current's difference, so it will have the shift and it will have the load angle part of it. So that's remember your currents will have your load angle. That's ironic in the delta that the currents also not the same, so also have the 30-degree shift. But your 30-degree shift for delta is minus 30 and not plus 30. So yeah, remember that, right? So yeah, so you're talking about the impedance angle. So lead lag, so this is impedance, R plus JX. So there's a calculation for the impedance angle and two important equations. You have XL, which is omega L, remember omega is 2 pi f, and then you have XC, which is minus 1 on omega C. Don't forget to put the minus. Yeah? And yes, so the impedance angle is equal to the power factor angle. So if they give it either one, it's the same thing, right? And we went through, which is the opposite for the star. The line current lags the phase current by 30 degrees. And the Y, the line current, leads the phase by 30 degrees. So anytime you're lagging, is minus 30. So for delta, there's a minus 30 degree shift between the phase current and the line current. Yeah? So that's the end of the source part. So any questions so far? Cool. Nice. So we can see. Yeah, so this just summarizes what we went through so far. So you take VAB as a reference, so your line voltages will basically be the same because in a delta is the same value. Notice no 30-degree shift because it's the same value. So it has be 0 minus 120 and 120 like normal. Your line and the phase is the same for delta. For the phase currents now, it will still be shifted, but you'll have to account for your power factor. Yeah. So basically just subtracting, in this case, subtracting the angle. Yeah. And then your line currents, so these here. So you have the 30 degrees in this one, minus for delta, and well, these here are your angles from your phase. Yeah. And that's basically it. And that is just a summary of it, right? And as I said, it's basically the opposite of the Y configuration. It's literally the opposite. For the delta, if you learn one, and when you do the other one, just know the I is like V and the V is like I. You just swap it. Just swap it. Cool. And then you go into some of the phases. So we know when you draw any phases, I like to draw my phases where this line here is always at 0. So this is 0. Some people will draw it in different ways. By all means, you could go ahead and try it, right? But in terms of the values itself, this is for delta. So for delta, the thing that will be different is the current, right? If it was a Y, the thing that will be different will be the voltage. So it does change in how this looks for each of them. So for delta, we know this IAA, the line leads or lags. So the lagging is there. So now you're looking at this here. So you have IA, IB, IC, and I put the equations so you all could see them. And then now, if you want to go back to this one. Yeah, this one will be at 0, your reference. So remember, you need to know the value of theta. So this whole phasor will shift depending on the value of your power factor angle. It will just shift. Yeah, so everything has the same thing as before. Don't forget to put in the 120 is in between. Yeah. Some y'all will draw it up in the kind of parallelogram way. That's okay. Nothing wrong with that. But just know when you're calculating the values, you'll need to know the values for IB and all them stuff. So if you're doing the phasor, in terms of the values, you want to see how you calculate. If you're plotting the currents, you don't want to show all the current phases and the lines. And if you're plotting the voltage, you want to see all the voltage phasor and the lines. Yeah. And if they say on the same, if they say plot the voltage and the current on the same graph, you could go ahead and do it. Also, it's all you doing how others do it. Others just ratchet, right? All I just do because I know the relationship between the lines and the phases for whatever configuration I have, I will literally just sit down and calculate the magnitudes, because you had the magnitudes from before, and just plot the phasors to get the angles for all of them. So if they want the um phasor, so I will have my currents for my phase, I will have the angles for them, and I will have the voltage for the phase, and I will have the angles for them. So once I have those two things, I will literally just sit down and just draw a sketch and just plot the phasors like normal. Because remember, you already have the values, Plotting the phasor is just implementing the values on paper via a sketch. So you will always have IA, IB, IC. You will have the magnitude fit and you will have the angle fit. Same thing too with IAB, whatever the case is. You will have the magnitude and you will have the angles fit. So if say to sketch the phasor, you just pick a reference and just draw everything with respect to that reference. Yeah. So once you do your angles correct, you will have no issues with plotting the phasor. If you have a mistake in your angles, then it will be a problem. Yeah.
I
Yeah.
have a question.
Yeah, going on.
So I was kind of get confused when it's time to differentiate between the phasor and the line current. Sorry, not the phasor, the line currents and the phase currents, right? And I think it's probably due to lack of practice. But
Which configuration?
so basically, I just asking if you have a way to get us somehow with differentiate it now.
Okay, so if I have a Y, so a Y configuration, if I draw a star and I draw lines coming out of it, that's what is right. Let's sketch it. So these are your line currents, no? So, and these inside here, and there's your phase currents coming out too. So inside here, there's your phase, and outside here is your line. You see enough? You're also
Yeah,
seeing that whatever coming out going straight into the line one time, it then splitting nothing. Come on, but
right.
this is like a ground here. So technically it's coming from ground straight up. So wherever A N is here, IA will be that exact value. You see now? From the time I sketch it,
Yeah,
I will know okay, yeah, that is a Y. So I will know from the time I go A is a Y, all the information come back. I know for Y, right, the line voltage, line current, sorry, is the same as your phase currents. They shifted 120 degrees apart spatially. Their voltages always will be different. So you have your phase voltages 0, minus 120, 120. Then to get the line voltages, you basically just add 30 degrees to each of the angles and multiply the magnitude by root 3. Because you know V line is equal to root 3 V phase. Remember that?
yeah.
From there,
Um,
everything
so
that.
the,
Go ahead.
as I said, if we go to the diagram for a second.
You want me to show the diagram or which one? The Y or the delta?
Yeah, the song will look.
This one?
Now, what's the next one?
So, this one?
Yeah, so like, yeah, right?
Mm-hmm.
How is the differential between the line and the
Right.
phasors?
Okay. So you have a delta configuration, right?
Right,
So in a delta configuration, you have three lines coming in. The names are those lines IA, IB, and IC. Now, so and that the names of the
right,
three lines, right? So this will be a IA, this will be a IC, and this here will be a IB. Now, so that's the
right.
names of it. And then you have to plot the phase currents now.
Phase current, which
You
is
have
numbers.
IAB, IBC, and ICA. Now, so by the tree. So IAB, because we know it lagging, so it will have a minus 30 degrees. Then you have IBC here, same minus 30. And then you have IC, ICA right here. You know?
Um, Actually, that was all I needed, yeah.
That's also, she just need this name. Once you name and convention there, he'll be able to plot it. But once
We
you're
could do
doing
it
the
faster,
calculation, go
just to
ahead,
be
go ahead.
sure. As I say, if we could do it over the same thing faster, just to be sure.
Yeah, but faster, the only thing I would change is that all these currents here, faster, is the same value. It's literally the same value. Because faster, the line currents and the phase current is the same value. So I could use this one. So the voltages, this is, I think this was about, yes, okay, yeah. So you see the phase voltages here. So that's where you're starting from,
Yeah,
right? Because realistically speaking, you'll have three single phase transformers that generate enough voltage and it's coming out, right? Oops, what did I do? That's not, yeah, how much cable is one? So you have three single phase transformers that giving you a voltage out. So if you're in a star configuration, one, two, you always start with the phase voltage. That is actually generated voltage, right? So you have VAN, VCN, and VBN, right? So in this case, those are your three phase voltages, VAN, VBN, and VCN. Obviously, to produce a three-phase power need to be shifted 120 degrees apart spatially, right? So we know 0 is for VA, VB is minus 120 and VC is plus 120, right? Just like before. You
Yeah.
plot these things here, right? So that's where you start.
So AN is the phase voltage and AB is the line voltage.
Yeah. So now, anytime you measure in between letters is line. That's how most of the time flows work. So you have VN, 120 this way could be VBN, which is minus 120, and 120 this way could be VC, which is at 120 degrees. And that's your phase. Get there?
Yeah.
And then look at one the line, well, now a few lines A to B, B to C, C to A. So the first thing I do is get the magnitude. So you just multiply the magnitude for the phase by root 3. So you expect the line to be a little longer because you multiply it by root 3, right? And then now,
Makes sense.
go ahead, go ahead.
No, I say that makes sense.
Right, and then for the, remember you had to do the magnitude part and the phase part, right? Because you need to do both. Now for the phases, because I know the line does lead the phase for the star, I need to add 30 degrees to each of your phase to get the line angle, right? So if I here, so VAN is at 0 degrees, right? So it'll basically be plus 30 here, plus 30 here, and plus 30 here, right? So 0 plus 30 is 30, no? So this VAB
Right.
will be at an angle 30 degrees. Then the next one is minus 120 and a plus 30. So that will give you VBC. So that will be at 90 degrees. So be here, right? Remember, this direction is positive, right? So this will be VBC angle 90 degrees. And this one here says 120 plus 30 degrees, right?
And the next degrees will be on the next side,
Well,
since the
no,
next
so it'll be
section
on
is
top.
negative.
Yeah, correct. Thanks. Good eyes. I'll leave this here for VCA. So this will be here. It'll be 120 and then plus 30 will be 150. Yeah, so you just gotta be careful when you plot any phase. It can get a little confusing sometimes because of how it's opposite to what it normally does. So this side is negative and this up here is positive, right? And I basically it. Just get lines.
So just to confirm, when you go in between letters, that's the phase.
If you go in between letters, that can be a phase. Remember, in a star
Right.
configuration. So if I measure
Okay.
between, like if this is VA here, VB here, and VC here, if I was to take a multimeter, which is impractical, just for explanation purposes, right? If I was to take a multimeter and pull this voltage here, and pull this voltage here, wouldn't I be measuring between the lines?
Yeah.
So that would be a line voltage, also.
Okay, good.
And so I can measure A to B, I can measure B to C, or I can measure C to A. All those will be three line voltages. But now, if I pull my reference and I measure from the reference to any of these points, I will get my phase voltage, which is why I have the end part that is capital.
Okay, yeah, so
And that is for the voltage. But for the currents now, it's still shifted 0 minus 120, 120, but you just have to know the load angle. Because the load angle will induce another shift in the phase. So it'll be the same concept, I is equal to I phase for the star, but the angle itself, while it still have the same 120 and minus 120 shift, you have to add in your load angle. Because current is a responding variable. So you have to calculate that. So if they ask, most of the time they ask to plot the phasor for the load. They won't really ask you to plot the phasor for the source. Yeah? Everything will be with respect to the load side, right?
okay, and usually this star is the source.
Yeah, usually this time you put a star and a source. The reason why you wouldn't put a source in a delta is because it don't have a reference point. So it will tend to be a bit unstable. and it wouldn't be able to handle unbalanced currents. Yeah,
So you more than likely be drawing a phasor faster.
I don't know, but more
Sorry,
likely,
but
yeah. Most likely. The source will most likely be a star, but the load could either be a star or a delta. So you have to prepare for both. Good? And for the deltas, is literally just the opposite. Whatever you do for I for the star, you just swap it. Because it's just the opposite. In the delta, the line currents are no longer the same as the phase. But the phase voltages is the same as the line voltages. Yeah? And with that, with the same understanding, I'm gonna just draw a table, right? To kind of summarize. So the first thing I have is the, so I had the delta. I have the star. So in the delta, right, we have same and we have difference.
now understand the formulas, understand the formulas, right? Differentiate that.
Yeah. But yeah, that's how I don't know which one the 30 degrees can be added to. The 30-degree shift will
Okay.
be added to the one that different. For delta will be minus 30, for star will be plus 30. You gotta remember that. Okay, if you leave that out when you're doing your calculations, you will get the wrong answer. The currents have the load angle in it for sure. You gotta remember that. But for delta, because the currents also different, it will have the 30-degree shift and it will have the power factor shift. So you have to remember those two. Current does always carry a power factor angle for the system itself. Yeah, in addition to being shifted by 120. So you have to keep track of your phasor angles. Yeah. So I just rather just do everything from the 0 minus 120, 120 from there. And then if I know I'm doing a delta, I'll go shift it by 30 because I want to go into the line and then do my power angle after. So that's what I remember. Okay, if you leave out one, it will make drawing the phasors harder. Yeah. I don't draw the phasors like with a diagram and thing. I just use my angles and just sketch it on paper one time. Yeah. It don't matter what I'm asking me to draw. Once I have my angles, there's a phasor. I could just realize it in a phasor diagram. Magnitude. 'Cause I think when I was doing the question, just remember, right? If one thing bigger than one, the line had to be longer, right? Because it's a phasor.
Yeah, I remember.
So that is very good there, right?
Yeah, we're there.
Cool. Alright, so I think we went through phasor.
You're doing on the table.
Forget it. I think I'll probably draw it next time. That's how I know currents does carry load angle in addition to being shifted 120 degrees. If you're doing a delta, you had to remember that you had to add in the 30-degree shift also. Yeah?
So to summarize, in a star,
Right?
you have the you have the power factor, which is the theta value,
So
and you have
currents.
yes, the current.
First our way to say in a Y, the currents are the same or
Yeah,
different.
in
The
a Y,
magnitude, yeah, the magnitudes for the
the current
currents
is
are
the
the same.
same.
Right? So the magnitude part will be the same, right? Now for the
Mm-hmm.
angle part, what is the first fundamental shift it must have?
First fundamental shift by 30 degrees.
Hmm.
No, no, the first the power factor, the
120.
120, yes.
That is first one. Then to go to the line voltage or the line currents, remember it's the same value for the Y. So you don't have any 30-degree shift there. You only use
Mm-hmm.
that 30 degree for the ones that are different. For Y, since the currents are the same, the voltage will have the 30-degree shift. For
Okay.
delta, since the voltages are the same, the current will have the 30-degree shift. The
Oh,
shift degrees that go with the part that different. Yeah?
okay. And it's always minus.
What I said?
They all be 30 for the phase online.
Phase and Well,
the 30-degree shift,
none would
depending on the
be the same.
configuration.
Yeah.
Yeah.
So for delta, since the voltage is different, that one will have the 30-degree shift. But not no power angle, because power angle don't go with voltage, right?
No.
Right. And then so go ahead and say what you're going to say. Why good?
So for the Y configuration, it's one start off with current, and current is I line and I phase. It's the same,
Mhm.
and then it'll be 120, and then the phase angle, which is only going on the voltage, which is 30 degrees.
Correct. But just remember, for the current, you will have the power angle shifting it
Mm-hmm.
also, right?
Right. So just the 120 minus whatever theta is,
Yeah. So the three
and
phases,
then
go ahead.
for delta, the voltage could be 120 degrees apart, but for the current, therefore not the same. So it'd be 120 minus the theta minus the 30.
Yes, minus the 30 for the delta and a plus the 30 for the star, right? Yeah, let's start to keep
Yeah.
track of your phases. Let's keep track. Yeah? You have to shift everything 120 degrees. Think of the shifting by the 120 degrees as putting it in the with respect to which phase it is. So if you shift something by minus 120 degrees, you'll be going into the B phase. If you shift something by plus 120 degrees, you'll go into the C phase. And well, I mean, the reference is the reference. So that'll be a phase, right? So, I mean, this slide kind of summarizing exactly where we went today, Bruno.
Yeah, I just making sure.
Yeah, for the current, for the Y is the same value. But you still have to shift it by the power angle. You notice all of them have the 0 degrees minus 120 and the 120. All of them have that. Okay, that is the fundamental shift. And for the line now, since it's the same value, no 30-degree shift. So it's literally the same value. You see now, right? It's literally the same
The
value.
reason why I asked that
Uh-huh.
is because going through it, most people, you see for the delta configuration, they don't include the other shift, which is minus 30 for the line.
Correct. And that is why most people will make that mistake and get it wrong. Yeah.
Thanks.
And well, for the voltages now, for the star, 0 minus 120, 120. But to get to the line, you have to shift it. So in this case, it's plus 30 degrees, right? And once I have these two things in my exam, if them ask me to plot the phasor for the voltage, I already have my magnitude and I have my angle. So I already know my default is this. I just use this one. So this could be my reference. I just plot everything from there. And I go on my way. So don't make the phasor plotting hard. It's based, you're just realizing it based on the phasor you have already. Yeah?
One last thing, right?
Yeah.
So it's only delta configuration is where V is plus 30. That's the only time.
When I say plus 30, Father,
Plus 30, I mean like you see how you have 0 minus 120 and plus 120?
this is our Y.
Yeah.
Uh-huh.
That is when it can be plus 30 degrees apart, not minus 30.
So in our delta, right? Your phase and your line it lagging. So just remember for our Y, right? This is our Y configuration. Y is plus 30 because your line does lead your phase. So for our Y, you will have the VAB here and you have the VAN here, right? So you're going in this way, so it's a 30-degree shift. So your line voltage does lead your phase voltage. So if something leading, you have to plus 30 degrees to shift it, right? For delta is the opposite. So you have your VAN here, and it's at the bottom now, which is a minus 30 degrees. Well, this will be current instead of voltage. So for the delta, it is because it's lagging, it will be minus 30 degrees. I think I have it in the next, will be minus 30 degrees.
I make that device.
Yeah, somebody saying
All
something.
this is provided the all this is provided the load balance.
What is he providing that here?
All the supply is provided that the load is balanced. So
It don't matter. You don't care. So the load on being unbalanced or balanced wouldn't affect the angles. The angles will account for that shift. So if you look at the angles, you'll be able to tell if it balanced or unbalanced. Yeah, but the balancedness of it have to do more to with the load part of it. So if you load balanced, everything else will be nice and even. Yeah.
Yeah.
But if you just do the question like normal, whether it balanced or unbalanced, all the values will work out for itself. Yeah. That's why it's the easiest part of it. 'Cause you don't have to shift anything. You don't have a shift for unbalanced system. It'll just work to account for it. So Vernon, you good? So just remember delta
Yeah.
minus 30 for the current. Because remember the current will be different, right? Remember guys, the
Yeah.
30 degrees goes with the one that different. For Y, the voltage different, so that one will have a 30 degrees. But that 30 will be plus. For delta, the current's different. So therefore that one will have the 30 degrees, but since it's lagging, it will be a minus. So you have to remember that, right? So are they good? Any more questions?
Just one last one, right?
Mm-hmm.
In the star, be let's say plus 30, right? But the
Right?
current will be minus 30.
Mm-mm. Think well. I repeat it slowly, right? The 30-degree
Mm-hmm.
shift goes with the one that is different. For Y, the line current is the same thing as the phase current. So you don't have to shift that. Y is shifting
Oh, I
slightly.
overthinking. I overthinking. Never mind.
It's
Never mind. I
they
read
will
that.
literally overlap each other. So you have no shift.
Yeah, I see. I
Yeah.
see what you're
So if you plot a voltage phasor for Y, you expect it to be different because you know the phase will
Yeah.
different from the line.
So
Yeah.
the current in the star will only be affected by the peak, the power factor, which is theta.
Correct.
Right.
Correct.
That makes yes.
And
I
that
was just overthinking it.
yeah, and it just shifted from the same minus 120 points.
Yeah.
Remember, everything have to the starting point for everything
Hmm.
have to be 120 degrees apart spatially. Yeah,
The only thing to note is exactly what you say. For the star, is plus 30 because it's leading. And
mm-hmm.
then for the delta, it's lagging, so it's minus 30 for the current. And the
Correct.
voltage for the delta will be equals to this 120.
Right. Plus 30 degrees. Yeah.
Yeah.
So plus 30 degrees for the voltage for the Y, and minus 30 degrees for the current for the delta. The opposite would literally
And
just be the same value. Mm-hmm.
for the delta voltage, right, it'll
Right.
just be 120 because have no theta to minus.
Correct. It have no power factor and thing for voltage.
Yeah.
So it'll basically be the exact same value, which is what else?
V line equals to V is
Right here.
equals to V line.
Yeah, because the same value.
Oh,
But yeah,
I just overthink it. Thanks.
that's okay. Just spend some time thinking about it. Once you remember, everything had to be shifted 120 degrees. The currents, whether you're doing a Y or a delta, the current does always have a minus theta, because that's your power factor. Yeah, just have to keep that in mind.
Yeah.
So
Thanks.
you're good. Alright, so I run into so could bring a question when he asks you to go from a star configuration into delta or delta into a star. So you basically have to remember these equations. So ZA, ZB, and ZC. So we're starting from a delta and you're going to a star configuration. So the easiest way to do it, or how I used to do it, I used to like to draw the resistor in between it. So this will be ZA, and this will be ZB and ZC. So, well, you have to do a line. That way easier to do. So in this case, you have ZAC, which is basically this one here. Then you have ZBC, which is this one here. Or you have ZAB, which is these here. So ZA now, if you're looking at it, ZA touching at this point, right? The red one is the delta. You're going towards the blue inside, right? So this one here, if you draw it inside here, So you're going towards the blue. So there's that. First one you start off with will be a ZA. So ZA, how we just think about it? The resistors that touching or connecting to the node will basically be the one they producting, and it always divided by the sum of all three of them. So for example, ZA will basically be ZAC multiplied by ZAB, and it divided by ZAC, ZAB, ZBC. If I wanted ZB, it would be ZBC multiplied by ZAB, because the two that touching here, and it divided by all three. If I wanted ZC, it would be ZAC, CBC, and divided by all three of them. So that we end up with the ZC, ZA, and ZBC. That's the easiest way I remember to do. Yeah, so you're seeing it. Seeing the pattern. So basically, we have the two that connected divided by the sum of all three.
In now I can remember too.
Sure.
You see numerator.
Mm-hmm.
You see like for ZA, the numerator have A and E in the numerator.
Right.
Right, to get ZA, you could think about it like you must have A and E.
Okay. Oh, and then the other two will be different.
Yeah, and then just divide by all.
Yeah, correct. Either way, but just remember, when you're doing it to verify, let's make sure the two that connect into it is the two that you multiply by on top. And you just divide it by the 3.
Um,
Yeah.
just to confirm, right?
Mm.
This is from a Y to a delta.
Yeah. But you're going from a delta to a Y. Because remember to say Y in terms of delta. Yeah, delta impedances will be AB, AC, and BC. So you notice that we
Okay,
kind of like,
good.
when this math express Y in terms of X, so the X will be all over on the right hand side, but Y will be the subject of the formula. The same thing here. So to go to
All right,
Y,
good.
that's ZA, ZB, ZC. So basically expressing the Y in terms of the delta impedances. So in this case, you're going, based on the arrow, you're going from a delta to a star. Cool. Everybody good there, right?
Yeah.
Yeah.
One. This is the opposite. So now you're going, you're writing a delta in terms of a Y. Yeah. So you have these here. It's basically the opposite if you can think about it. So you're going from a ZA, ZB, ZC form into a delta. AB, AC, and BC. So delta in terms of Y, so the right hand side could be A, B, C, and the left hand side would be your delta impedances. So ZAB, if you see the pattern, ZAB, ZAB, CAC, ZAC, ZBC, you have BC there, and the other two always there, which is just the opposite of this. You just end up on the numerator, and then you're just dividing by the opposites. So for ZAB is ZC, ZAC, B, BC, A. Yeah? There's always the letter that not here. Yeah? So if I wanted to do ZAB, it could be ZAB, you have ZAC, and then you have ZB. Well, it don't matter because they multiply. Yeah, you're multiplying them. So multiplication is commutative, so it only matter the order. And they divided by the letter that not here, which in this case is ZC. I let's repeat the same process. If I wanted to do AC, it could be ZA, ZC plus ZA, ZB plus ZB, ZC. I divided by the letter that not here, which is ZB. And that's it. Right? Any questions on that? So that's how you go from a start of it. Cool. Well, yeah.
The question I have is which year this question came into practice with?
I don't show off the top of my head. I can't get the answer off the top of my head, so I don't know.
So I mean,
2024
yes.
about question with it.
Yeah.
Okay, good. 2024, right?
Yeah, the for revision on thing.
Yeah, you have it in the review section in the tutorials stuff.
Yeah.
All right, thanks.
Mm-hmm. Everybody good there? Right,
Yeah.
so we move on. Well, if it's a balance load, your Y impedance will basically one third of your the delta impedance. But as for balance, everything is the same now, so everything is going to reduce. So this is important. So if you have a balance load and you want it to go from a delta to a star or a star to a delta, you could just use this to transfer it quickly. Yeah. So if you're going from a Y, sorry, if you're going from a delta to a Y, the Y impedance for each of them would just be one third of one of the delta impedances. Yeah. Even if you don't get that, you just go back to first principles and do the long equation. Either way, you get the same answer. Alright, cool. So again, to the power side of it. So the first thing you have to know is something called a power triangle, right? Because you could ask you to draw the power triangle for a system. Less likely, but it's still there. So a power triangle now, you have your phase angle, which is called a power factor. There's a phase angle there. Then you have on the horizontal piece, you have your real power, which is VI cos theta. Then you have your reactive part, which is Q, which is VI sine theta. Then you have your apparent power, which is VA, which is just VI. They basically expressing the VI in terms of the horizontal and vertical component. So there's your real power, reactive power, and apparent power. And the part that merge all of them together in the complex domain is S is equal to a real power plus J by a reactive power. This will change depending on the type of load they have. So if this is octave and then you have SP minus JQ, the capacitive. So it depends on the type of power. Because a capacitive circuit does add negative Q. Yeah, and an inductive circuit does add positive Q. So let's keep that in mind. Alright, cool. Next one is the equation for power. Luckily, it's the same thing for Y and delta configuration. It's literally the same thing. 1 and root 3 V line I line cos theta. Same thing for both of them. Yeah, which is the beautiful part. Because you don't have to remember two equations. You just have to remember one. 1 and root 3 magnitude of V line, magnitude of I line cos theta. What that means is you don't put the angle in this calculation. Just the magnitude. A lot of people just put in the angle in it and get wrong. Just the magnitude, the part you put in. So that's the real power. And the next one is the reactive power. The only difference with the reactive power is that instead of cos theta, is sine theta on this side. So the sine theta is still reactive. Cos theta for real, sine theta for reactive. Alright, and well, merging all them together, a bit of Pythagoras theorem. S squared will equal to the square root of the horizontal squared plus the vertical squared, which would just give you root 3 V line I line, no angle. Notice this root 3 on top, not 1 over root 3. Yeah, so remember the triangle itself, you have S, P, and Q. So from Pythagoras theorem, S squared will equal to P squared plus Q squared, and you just make S the subject of the formula. That is it, that is how this is. And then this is just the same equation, but without the angle. And then one more to, there's some important equations that you probably will come across while you're doing it. So we know the inductive reactance is omega L, remember omega is 2 pi F. You have the capacitive reactance, just know they have a negative here, because minus J on omega C. You have your impedance. Just remember, when you're doing the impedance now, it will be R plus J, XL will be positive, minus XC. There's always XL minus XC. Yeah? Because the capacitance will be negative. So when you add them up, XL minus XC or minus XC plus XL, just note that the capacitance, the reactance for the capacitor or the reactive capacitance, anything I want to say, is negative. Power angle, we came across this already, is just tan inverse. So if you have Z here and you have R here and you have X here, if you want to take the angle, so this will be opposite adjacent, so it will be tan theta, just normal trees. So it will be tan inverse of X on R. Yeah. And then well, eventually real power already. This is just splitting it up into the two components. So once if you have Z and the power angle, they could get R and X. Those are tricks. Yeah. And then this one here real popular, because most of the time you sort of use this first when you're doing the questions to get Z. Once you have Z, I, most of the time, you will have an angle for I. Remember, the angle for I is the power factor. So you just have to remember that. A lot of people just forget that. So the angle for the current is the power factor. Just note, use the reference current. So meaning the reference current is the one that measured from 0 degrees. Because if you use any other one, you will have to bring it back. Because the power factor have to be smaller. So always use the one that measured from 0. So yeah, voltage most of the time is always at 0 degrees. And if I phase will also have your power factor or your load angle, all that be the same thing. So let's keep that in mind. You always have the angle for the current, especially for the reference piece. You always have that. From the time they give you power factor is, they indirectly giving you the angle for the current for your reference. And if you want the other three phase currents, you just shift it by the 120 degrees from that value. So for example, if the city power factor is 0.8, right? Somebody could tell me what the cos inverse of 0.8 is.
$36.86 or 87.
Cool. So if it's 36.87, the next thing I must tell you is if it's a lead or a lap, or if it's a capacitive circuit, inductive, I must tell you that. So if this is a capacitive, it will have a negative here. Or let's say lag, so it'll be a negative. So they're not going to tell you the sign here, right? We're not going to get the sign from the calculation. They'll have to tell you the type of load it is. If this is a capacitive load, negative current. Inductive, positive. Just keep that in mind, right? So right, so we have minus. So therefore, the reference current, like we say, is 10 amps. I will be 10. How we will get I? Most of the time you had to use this equation here for the real power. Because it does give you P, does give you V line, does give you I line, and they'll give you the cos theta, right? So you could just transpose for I line. And depending on the type of configuration it is, you will know if you have to multiply that by, well, divide that by root 3, or it be in the same value. Yeah, so back to here, this will be minus 36.87, so that will be the current. From that current, this is in a reference. If I want the other two phases, the currents for those phases are just shifted by 120. So if I want to go to C, a plus 120 degrees, and if I want to go to B, a minus 120 degrees from this. And you only do that in a delta configuration. Yeah, and a star if you want to get it. So from here, you could go anywhere you want to go, depending on the configuration. Everything you do here when you plot in the phase and stuff is with respect to the type of configuration you have. Always keep that in mind when you do any question, especially with three phase. Know the type of configuration you have. Yeah. So cool. Well, that really the end. That's really the end there. So you have any questions?
Don't think so.
I really don't. So Alright, so y'all should know how to plot the phasors. The plotting the phasor part is just knowing the angles. At the end of doing all the calculations, you will have the magnitude for the voltage and the current. So, and the phase angles for them. From those three things, you could go anywhere you want, depending on whatever they ask you for. Just read exactly what they ask you to put in the phasor. Sometimes they just say the line, voltage, phase, just read it properly. Sometimes they say both line and phase. Just do it piece by piece and plot. There's good marks you could get. And you just have to know the differences between the angles. So I urge you to go through this and make sure you master the phase angles and stuff. And then try. So what I'll do during the day, I'll send you all a 3 phase question to do now. Try it, send me a picture. So you have to go ahead and start the study. If you need help with anything, you can make sure and message me, right? But I'll make sure and I'll be sending you a question during the day to practice. So you all keep any scribbles or no scribbles?
I think it needs
Let's
to.
Cool, let's stop the recording.